Hello, welcome to the course Two-Phase Flow and Heat Transfer. Today we will be going for 17th lecture and the topic of our lecture today is boiling heat transfer. At the end of today's lecture, we will be understanding the differences between pool boiling and flow boiling. We will be also understanding different regimes of pool boiling heat transfer along with its boiling curve. We will be also finding out that how departure radius of a bubble varies with degree of superheat. We will be also seeing that how heat flux can be evaluated when the bubble is growing in pool boiling situation. We will be seeing how flow boiling and how flow boiling occurs inside a pipe and its corresponding boiling curve. We will be finding out the methodologies for calculation of flow boiling heat transfer. Let us quickly see what is boiling heat transfer. Actually, boiling describes the process in which you will be finding out addition of heat is causing change of phase from liquid to gas. Okay. Now, boiling, if we try to define or categorize, then we will be finding out it can be divided into two broad classifications. Those are pool boiling and flow boiling. Pool boiling is associated inside a stagnant pool where liquid flow is not predominant. Okay. So, mainly you will find out flow is causing due to natural convection and whatever flow pattern is causing, that is driven by heat transfer. On the other hand, if you see flow boiling, the flow boiling will be guided by the fluid movement. Inside the pipe, you will be having the movement of the fluid and that velocity of the fluid will be defining what flow regime will be occurring inside. Obviously, heat transfer will be taking major role in the flow pattern inside flow boiling also. So, let us see next that what are the common mistakes we do while we define boiling heat transfer. So, basically boiling is actually phase change and which can be talked as a vaporization process. So, vaporization is nothing but conversion of liquid into vapor by applying heat. Now, if this vaporization is occurring only at the surface of the liquid, we will be calling that as evaporation. Okay? And if we find out that boiling or vaporization is happening throughout the pool, okay, inside the bulk of the pool also, liquid pool, we are having the phase change, then we will be calling that one as boiling. Okay. So, there is basic difference between evaporation and boiling. If the phase change occurs only at the surface, free surface, that is called evaporation, and if it is a volumetric phenomenon, then it is called boiling heat transfer. Okay, here I have shown typical examples for boiling heat transfer. So, this is macroscopic analysis, you can find out the water is boiling in a pictorial view, and here I have given you some sort of particulate understanding. So, here inside we had close compaction of the molecules in the form of liquid, and once you add heat, you will be finding out some molecules will be becoming widely packed and you will be finding out those are coming in the vapor form. Okay. Now, our common understanding about boiling heat transfer is that whenever the temperature of the fluid and gas will be coming equivalent to the saturation temperature of pressure, that will be the limit from where boiling will be starting. Okay. But eventually we will find out that due to this molecular compaction difference, the pressure of the vapor will be higher compared to the pressure of the liquid. So, you can find out Pg, which is the vapor pressure, is higher than the Pf, which is the liquid pressure, right. As the pressures are different, we will be finding out that liquid temperature and vapor temperature, they are not similar. You will find out that liquid temperature is more or less equivalent to the saturation temperature corresponding to the vapor pressure. Okay. Now, what is the saturation temperature corresponding to this vapor pressure? We have already understood in thermodynamics. So, you can find out for any substance, even for water also, what is the saturation temperature corresponding to this given pressure. And we know that temperature is actually, saturation temperature is actually proportional to your pressure. So, you will be finding out as vapor pressure is higher than the liquid pressure, saturation temperature corresponding to vapor pressure will be higher than the saturation temperature corresponding to liquid pressure. Okay. So, if you think about equilibrium when boiling is happening and once again pool is coming into equilibrium position, then you can write down that saturation temperature T sat, okay, del T sat is equals to Tf minus T sat Pf. So, this Tf is nothing but the fluid temperature and T sat Pf is saturation temperature corresponding to the fluid pressure, will be equals to Tg minus T sat into Pf. So, basically these differences between the saturation temperature and liquid temperature for both the liquid and vapor phases will be equal, and that we will be calling as delta T saturation, right. Next, let us see that how pool boiling heat transfer occurs. We will be starting with the first regime, which is pool boiling heat transfer. So, at the beginning you will find out inside the pool we will be having only natural convection, okay. We have already understood what is heat transfer, so we know what is natural convection. We will be finding out that as the surface over which the boiling is occurring, that is hot, then you will find out that the liquid will be having some circulation cells like this, okay. Heavier liquid is coming down, taking the heat and once again moving up, okay. So, there will be circulation cells inside. Now, very soon you will be finding out that over the surface, when the temperature increases, you will be finding out that small sized bubbles are being generated at the nucleation sites. So, this is actually a you can call this one as second region and we can call this one as partial nucleate boiling. So, this you can say that this is the initiation of the nucleate boiling. In this zone you will be finding out lots of smaller bubbles are over the surface, and you will be finding out that those bubbles are actually departing from the surface whenever it gets a finite amount of size. What will be the size depending on the degree of superheat, I will be discussing soon. Next, you will be finding out a zone where lots of bubbles are being generated from a surface from a nucleation site, and you will find out those bubbles are generated so fast that they are forming a bubble train. So, here I have shown one example of bubble train, you see, and if the bubble train is very closely spaced, that means fast bubbles are being released from the surface, you can find out there is vertical margin and a long film also can be protruded from the nucleation site. Now, soon as you increase the heat transfer and as you increase the degree of superheat of the surface, then you will be finding out these films are being merged with each other, or it can be starting from this region 2 also. Bubbles will be forming more in number over the surface because nucleation sites will be becoming activated more and more in number, and you will find out those bubbles are merging with each other and they are forming a horizontal film, okay. So, in this transition B you will be finding out vertical film, and here you will be finding out horizontal film, okay. Then at some position you will be finding out that there is no more scope of fresh liquid to come in contact with the solid surface, and you will be finding out that moreover the surface is occupied by the gaseous phase. So, this we call as transition boiling, okay. And at the end you will be finding out that whenever these vapor films are also merging with each other in the horizontal direction, the whole surface is occupied by the film, and you will be finding out a zone which is called film boiling. Now, let us try to see the boiling curve. Boiling curve means how heat flux varies with degree of superheat. Here I have shown a typical curve. You can find out in the first zone, which is called a natural convection zone, you can find out as we increase the degree of superheat, heat flux increases, but in this zone essentially you will not find out any formation of bubble. Then after that, A to B is actually our region 2, where you will be finding out smaller bubbles are being generated on the surface, and with degree of superheat, heat flux will be also increasing. Later on, from B to C you will be finding out that we are having horizontal merging of the bubbles and formation of this kind of horizontal film, bigger bubbles in the horizontal direction you can find out. At point C you will be finding out maximum heat flux has been reached, and you will be getting from this point there will be sudden shift of temperature in case of heat flux controlled experiment, okay, because you will be finding out after reaching at point C, the whole surface is actually covered by film, and suddenly the temperature of the surface will be increasing. So, this point is actually very critical. From here the temperature suddenly shoots up. So, this is actually called critical heat flux point, okay. So, after that we will be getting at the same heat flux, we will be having a huge change of degree of superheat suddenly, and finally you will be finding out after point E we are having overall film over the surface which is region 5, and due to your gaseous convection you will be finding out as degree of superheat increases, heat flux will be also increasing over here. So, this curve is always increasing in nature. Okay, so, in case of heat flux controlled experiment, you will be finding out this sudden jump of the temperature, okay, while you are increasing the heat flux, and if you do the reverse, that means if you reduce the heat flux continuously, then you will be finding out it will be starting from the film boiling, it will reduce like this, come over here at the minimum point which is called actually leaden frost point, okay. In this leaden frost point you will be finding out film is actually breaking into smaller small bubbles, horizontally small bubbles, and at this point you will be finding out that there is a sudden drop of the temperature, and film is forming smaller bubbles over the surface, and then once again a small zone of nucleate boiling, and finally your convection continues, okay. But in case of your temperature controlled experiment, this type of sudden jump or drop will not be observed. You will be finding out that for a particular temperature you are having a particular heat flux, okay. Right. Next, let us discuss about nucleate boiling heat transfer under pool boiling section. So, here I have shown a typical nucleation site. So, typically nucleation sites are surface roughnesses. So, you will be finding out those are very irregular, but to standardize what we do, we take a nucleation site like this one. Here I have shown a V grouped surface. So, you see this is your nucleation site. So, here at the beginning whenever bubble is forming, you will be finding out that the lowest position of the nucleation site is acting at as the centroid of the vapor. So, you can find out here, you see if at the beginning this is the gas liquid interface. So, you can find out its centroid is somewhere over here, okay. So, this arc is somewhere over here, okay. So, you can find out this is below the domain of your nucleation site. As it increases its volume, you can find out this interface will be moving in the outward direction, and after some time you see it comes to the limiting zone when the interface corners has touched the free surface. Free surface means solid surface, okay, the outer periphery of the solid surface. So, you see this is the point where the outer plane surface is actually coming into picture with the nucleation surface, okay, nucleation site. So, you see this is the critical position. So, over here also you can find out it is making some radius with the same center which is far below than the nucleation site, okay. But after that immediately you will be finding out when the vapor liquid interface has protruded outside the surface, you will be finding out that it is getting more and more space to grow circumferentially in a spherical manner, and you will find out that this growth is unconstrained in the pool, and you will be finding out that the center of mass, or you can say the center of curvature for this interface will be slowly coming up, and you will be finding out at some point of time it will be coming up even above the solid surface. So, here I have given typical example R4 you can see, which is out above the horizontal surface. Now, if one tries to plot that this variation of the curvature 1 by r with respect to the vapor volume, he will be finding out, he or she will be finding out that at the beginning phase there will be a fast reduction of the curvature from 1 by r1 to 1 by r2. Here r1 and r2 both I have shown. So, bubble will be actually increasing, but bubble will be increasing the volume, but you will be finding out that this radius will be also increasing, okay. So, as a result 1 by r will be decreasing, okay. Then after a critical point you will be finding out there is once again a slow rise. So, this slow rise is due to from 1 by r2 to 1 by r3. You can find out over here r2 is higher compared to r3, 3, so obviously 1 by R3 will be higher, okay, and you will be finding out a rise in the curvature, but this rise will be slower compared to the fall of 1 by R2 to 1 by R1. Then after once again rating a critical point, it will once again fall very fast, which is nothing but between 1 by R3 to 1 by R4. The important thing is here 1 by R3 to 1 by R4 is this one, that at this domain the center of the curvature is actually center of the interfacial periphery will be actually coming out of the surface, okay, and it happens very fast, okay. So, this is a typical bubble growth behavior and its center of curvature, radius of curvature we can plot with respect to volume. Okay. Then let us see that how this radius of curvature, or you can say the radius of bubble varies with respect to your degree of superheat. Okay. So, to give the idea of that, we will be taking a bubble, let us say this is a bubble which we have cut from the middle plane, and you can find out that we are having two different forces over here applicable. First one obviously the pressure force, because the gaseous pressure will not be equivalent to the liquid pressure, already we have explained in the previous slide, and we will be also finding out that surface tension plays a major role okay, to make the circumferential periphery. So, we will be trying to balance the pressure force and the surface tension force. So, if you do so, here you will be finding out Pg minus Pf, which is the pressure drop between across the surface, okay, multiplied by pi r square, and this is equivalent to pi into 2 pi r. So, pi into 2 pi r will be actually sigma into 2 pi r, sigma is the surface tension and 2 pi r will be this perimeter of this circle along which the surface tension will be acting. So, if we balance these two, then we will be finding out Pg minus Pf becomes 2 sigma by r. Okay. Then let us take the help of famous relationship given by Lord Kelvin from his Kelvin-Helmholtz instability. He proposed that if we are having some curvilinear interface, he proposed that Pg can be written as P infinity, where P infinity is the pressure of the bulk. Okay, so that will be the bulk pressure in the liquid. So, P infinity into e to the power minus 2 sigma Vf m is the molecular weight, okay, for the gaseous phase, divided by r star. R star is nothing but your radius of the bubble, and then r bar is the universal gas constant into T. Okay. So, from here if we try to replace this m by RT with your pressure and volume using PV equals to MRT for the gaseous phase, then I can write down Pg equals to P infinity into 1 minus 2 sigma Vf by R into 1 by P alpha P infinity into Vg. By the way, here we have already taken the assumption that e to the power x is actually equals to 1 plus x plus some higher term which we can neglect. So, we have neglected the higher order terms over here. Okay. So, here we are having e to the power minus x, so this 1 minus x comes into picture. Now, from here we can get that Pg minus P infinity is equals to minus of 2 sigma Vf by R star into Vg. So, now here you see we are having two pressure differences. This is the pressure difference between the gaseous phase and the liquid phase, and this is the pressure difference between the gaseous phase and the bulk. So, you can find out this, we can easily use, and we can find out the relationship between the bulk pressure and the immediate near liquid pressure of the interface. So, we get, if we subtract those two equations, whatever I have shown you in the previous slide, we will be getting 2 sigma by R star into 1 plus Vf by Vg. Okay. Next, let us see how we can simplify it further. We will be taking the help of famous Clausius-Clapeyron equation. So, we know that Clausius-Clapeyron equation says del P del T at saturation is equals to Hfg by T sat into Vf minus Vg, right. So, sorry, Vg minus Vf, right. So, here I will be considering that your vapor specific volume is very high compared to liquid specific volume. That means we are talking about a fluid where density ratio is very high. Perfect example is water. Okay. So, here I will be considering that Vg is higher compared to Vf. So, what we can do, we can neglect this Vf and we can write down Vg minus Vf is equals to Vg. So, we get subsequently this del P by del T sat is is nothing but HFG by Tsat into Vg. Okay. So, if you continue further like this, then we will be finding out that del P by del Tsat is equals to HFG by Tsat, and then you know this Vg I can convert using PV equals to MRT formula once again, then I will be getting back HFG into MPR, and two temperatures will be multiplied now. One was already there in the form of Tsat, another one will be coming due to your Vg, so we will be getting T square over here. So, now here you see in the left hand side we are having dP and dt, here we are having a function which is pressure and dependent on pressure and temperature. So, we can start integration procedure. So, we have integrated over here dP by P, and the limits will be Pf to P infinity, and here in the right hand side we have integrated with respect to T, and the limits will be Tsat to Tg. Once we go for this integration, then we will be finding out that ln P infinity by Pf is equals to minus of HFG m by r into 1 by Tg minus 1 by Tsat. Okay. Further simplification if you do, then you will be getting this kind of equation. Now, from here I can get what is Tg minus Tsat. So, Tg minus Tsat, so obviously that will be this multiplier will be going in the other side, and we will be getting this is R Tg Tsat divided by HFG m ln of this term. Okay. This term once again, see there was ln of P alpha by Pf. So, P alpha by Pf already we have shown you in the slide over here what is P alpha by Pf. P alpha by Pf, if you see over here, that will be 1 plus of this term. Okay. So, that we have put over here 1 plus of 2 sigma Pf r star into 1 plus Vf by Vg. Okay. Let us take further assumption to make it simpler. Once again the same assumption that Vg is higher than Vf, and let us consider that 2 sigma by Pf into r star is very small. Okay. So, if this is very small, okay, and this is actually Vf is lower compared to very lower compared to Vg, then we will find out Tg minus Tsat simplifies to this equation. Okay. R Tsat whole square by HFG m into 2 sigma by Pf r star. Okay. Further simplification of this one gives us delta T equals to 2 sigma Tsat Vg by HFG r star. So, you can see over here that delta T is actually having inverse relationship with r star. So, this gives you some sort of idea that what will be your bubble radius whenever we are having variable degree of superheat. Okay. So, this equation is very important for finding out the departure radius of a bubble. Okay. Next, let us try to see when the bubble is growing, in that situation what happens in case of nucleate boiling. Okay. Now, bubble growth in nucleate boiling can be classified into two portions dependent on the time. So, first portion is actually called initial growth period. Okay. In the initial growth period, you will be finding out that always below the bubble we will be having a thin liquid layer, wedge shaped liquid layer. On the other hand, after a initial growth period Tg, you will be finding out we have final growth period, where you will be finding out that we are having two layers. Okay. The first layer was actually termed as micro layer, and in case of second growth period, you will be finding out apart from micro layer we are having another portion which is called macro layer. Okay. So, here you can find out this was micro layer, and over there here we are having macro layer. At the junction of macro layer and micro layer there will be change of radius of curvature. So, the curvature will not be continuous at the junction of macro layer and micro layer. Okay. Now, if we try to figure out that what will be the heat flux during this bubble growth period, so let us take this figure for example. Here I have shown you this domain is actually liquid layer which is called micro layer, here we are having macro layer. Apart from that, we have also considered a region which is called a dry out region, where liquid is not in contact with the solid heater. So, if we consider all these three regions apart from the outer periphery also of the bubble, okay, into consideration, then we will be getting that heat flux will be becoming 0 for the dry out region, because there is direct contact between the gas and solid surface, and in the micro layer and macro layer region we can find out minus rho f HFG into d delta by dt, and micro layer thickness and macro layer thickness will be coming into picture over there, okay, because mass loss will be directly proportional to the thickness of the layer loss, okay. So, here this will be varying from different radiuses. You see this is RD was actually the dry out region, D by 2 is actually your extreme limit of the micro layer, RC is your extreme limit of the macro layer, and finally your this capital RD was the bubble diameter, okay. Now, here I have shown you what will be happening whenever we integrate this one over the limits of this one. Here it was zonal based heat flux I have shown, instantaneous and at a particular position. If you integrate, then you will be getting this equation. For the first and second we will not be getting anything. So, here we have written 0. Sorry, for the first we will not be getting anything, but here, here and here we have to integrate depending on the area that we have done. Okay. Next, let us see that in case of nucleate boiling, what type of correlations are available. So, the best known correlation for nucleate boiling heat transfer is Rosenau correlation. So, in case of Rosenau correlation, you will be finding out that we are having lots of empirical constants also over here. Okay. So, you see Rosenau correlation is QNB, which is the heat flux in the nucleate boiling zone, and it is actually connected with this del TW minus Tsat, which is nothing but your surface temperature. So, here other properties are fluid properties, which you can find out from the specific fluid combinations, but CSF and N, these two are the empirical constant, and Rosenau he has given a wide variety of fluids and he has mentioned that what will be the constant values. For water, one can use CSF equals to 0.013 and N equals to 1. Okay. Similarly, it is also very important to predict the critical heat flux, just like your nucleate boiling heat transfer. So, critical heat flux will be CCR into HFG, okay, rho sigma into G into rho G square, rho minus rho G to the power 1 by 4, and this correlation has been given by Kutatelaj, okay, in 1951. Here CCR is the empirical constant, and he has proposed empirical constant can be taken as 0.149. Similarly, for film boiling region, we are having lots of correlations. The famous one is Bromley's correlation. In 1950, he has given this correlation. Here also you see we get the film boiling heat flux as a function of TW minus Tsat, which is your surface superheat. So, all other properties are actually fluid properties. So, you can find out fluid combination properties you can find out, and total heat flux in case of film boiling can be written as Q film over here plus 3 by 4 Q radiation, because in case of film boiling surface temperature will be very high. So, radiation cannot be neglected. So, radiation heat transfer also we need to calculate. In this fashion I have shown, this is very common to all of us, how radiation heat flux can be considered. Okay. Next, let us see something about flow boiling. In case of flow boiling, we know this figure is known to you already, I have shown you in the first lecture. So, that if we start heating a pipe, okay, in which water is or some liquid is going on, then you will be finding out at the beginning we are having bubbly flow, small bubbles are being generated, then all those bubbles will be merging and forming a slug bubble. Then we will be finding out annular film over here. Okay. So, in the wall you will be finding out inside the tube, in the wall you will be finding out liquid, and then we will be finding out annular flow with entrainment. This also we have discussed in detail, and finally we will be having droplet flow, which is more or less similar to this bubbly flow, but in reverse manner. Okay, and at the end you will be finding out once again a single phase flow. Few important things we need to notice over here is that at some point of time you will be finding out the dry out of the pipe. Okay, so this is the point where you will be finding out the pipe is not in contact with the liquid. So, we will be having a dry out at this point, and at this point you will be finding out that wall temperature is suddenly increasing. So, you see up to this we are having a constant temperature, almost constant temperature, and whenever dry out occurs there will be a sudden increase of temperature, okay, for the tube wall. So, this is very typical feature for your flow boiling condition. Now, flow boiling curve, if we want to plot, that means Q versus delta T sat plot, if you want to do for flow boiling, then you will be finding out the curve looks like more or less same, having the natural convection, nucleate boiling, and then finally critical heat flux, and then film boiling. But obviously due to the flow, whatever you are having, the heat transfer coefficient will be increasing, and you can find out that flow boiling curve will be in the higher side in comparison to the nucleate boiling or pool boiling curve. Okay. So, here also we can see the single phase convection, then nucleation, then transition, finally this is your dry out or critical heat flux, and then we are having a part where we are having film boiling, as I have discussed earlier. Next, let us see in case of flow boiling how we can find out the heat transfer coefficient. There are few correlations. The famous one is called Kandlikar's correlation, who has given the correlation in 1990. So, he has mentioned that two phase flow boiling correlation heat transfer coefficient HTP can be found out as H multiplied by C1 CO to the power C2 multiplied by 25 Froude number LO liquid only to the power C5 plus C3, and this is boiling number. So, boiling number to the power C4 and FFL. Okay. So, here CO is actually convection number, because you know in flow boiling convection will be important parameter, and BO is the boiling number, which is important for boiling heat transfer. FL is the fluid dependent parameter. So, what Kandlikar has proposed, he has proposed all these empirical constants C1, C2, C3, C4, C5, all these empirical constants he has proposed for convective region and nucleate region like this. So, you can pick up this value and always find out what is the two phase flow heat transfer coefficient. Similarly, in case of film boiling, in flow boiling situation, one can find out the heat transfer coefficient in this fashion. So, heat transfer coefficient Q double dash will be alpha 2 phi Tw minus Tsat, and this alpha 2 phi can be found out in this fashion. All these things are actually fluid dependent parameters apart from G. So, once you know the value of the flow rate, you can find out the value of G. All these here you can find out are fluid dependent parameter. Only this Tw minus Tsat is actually your degree of superheat. Here we are having empirical constants also, this F and S. So, F and S can be found out in this fashion. F is 1 for this limit whenever it is very higher value of two phase friction factors, and if for lower value you will be finding out this one. Okay. S can be found out in this fashion, where it is once again dependent on F and the film Reynolds number. Film Reynolds number can be defined in this fashion. Okay. He has he has defined this two phase multiplier in a different way. So, he has defined this one with some power over here. Earlier we have seen this is 1 minus x by x, rho f by rho g and mu f by mu g, but he has given some power over here 0.9, 0.5 and 0.1. So, this change correlation will be very important for finding out the heat transfer coefficient in film boiling. Let us summarize this lecture. So, in this lecture what we have done, we have discussed about pool boiling and flow boiling situations. We have found out the departure diameter for a bubble whenever we are having different degree of superheat. We have found out popular correlations in case of nucleate boiling and film boiling, and finally we have found out that what will be the flow boiling empirical constants in case of your chain and Kandlikar equations. Okay. Let us test your understanding at the end of this lecture. So, here we are having 3 questions. Phenomenon of boiling occurs. We are having 4 answers: only at free surface, at gas solid interface, at lower temperature than saturation, and throughout the liquid pool. So, this we have mentioned in 3rd slide of this lecture. So, answer is throughout the liquid pool. Okay. So, if it is only at the free surface, then that will be your evaporation. Okay, next question, necessary conditions for boiling. So, we are having 4 answers: Tw less than Tsat, Tw is equals to T critical point, Tw greater than Tsat, and Tw is equals to 0 Kelvin. Okay. So, I think all of you know the answer. So, answer is Tw greater than Tsat. Okay. 3rd question, heat transfer coefficient in flow boiling is higher than pool boiling, lower than pool boiling, depends on the inclination and depends on pipe geometry. Okay, already we have compared using a graph how the heat transfer coefficient is actually dependent on in pool boiling and flow boiling situations. So, obviously the answer is higher than pool boiling. Okay. So, with this I will be ending this lecture. Thank you.